In this video, we pick up where we left off in the last video by discussing three equivalent ways to view the same problem. So the first way is to think of m linear equations in n unknowns. So I've got a first equation, a second equation, a third equation, an mth equation. M could be 5, so then that would mean there are 5 equations. N could be, or M could be 3, so there would be 3 equations. But in general, there are m equations. We'll call that the mth equation. And we have n unknowns, x sub 1 through x sub n. Now, if these a sub 1, 1, and a sub 1, 2, and a sub 1, n, if all of these a's are constants, usually they're real numbers, and the b sub 1 through b sub n are real numbers, this is a system of m equations and n unknowns, and our goal is usually to find x sub 1 through x sub n that causes this system of equations to be satisfied. Now, in the last video, we said if we have a system of equations that looks like this, we could rewrite it in this way. Now, I would like you to notice what I've done. I have just looked at the entries in every equation that involve x1, and I factored that out. And then I said that's x1 times the vector with components a sub 1, 1, and a sub 2, 1, and a sub m1. Notice that that second number in the subscript is a 1. We're going to call that the vector a sub 1. And then similarly, we're going to say if we take that and we multiply it by x1, and then we take this next vector and multiply it by x2, notice again the entries. This is a sub 1, 2, and a sub 2, 2, and a sub m2. So the first number changes from 1, 2, 3, and so on, and it counts down to m. And then the second number is always 2. We're going to call this the vector a sub 2. The next one, very similar, the second subscript is a 3. The first subscript goes from 1 to m. We're going to call that a sub 3. And then the last one, we'll call that vector a sub n because there are n of them. And we'll call this the vector b. I hope that you can see that if you take this vector and you multiply by x1, so that each of these numbers is multiplied by x1, we get that. And if you take this vector and multiply by x2, if you do that, the vector will look like that right there. Those will be the entries of our vector. And if you continue to do that and then you add all of those together, you're going to get the expressions on the left-hand side of those m equations. And then the right-hand side of those equations is given by the vector, the entries in the vector b. So we've got a system of m linear equations and n unknowns x sub 1 through x sub n. In the last video, we said that we could take that and we could write it in this way. So this is x times a vector a1, or x1 times a vector a1, plus x2 times a vector a2, plus x3 times a vector a3, and so on. So let me just write that in shorthand. The unknowns here are the x sub 1 through x sub n, and we see that we have a linear combination of vectors. This is a constant times a vector plus a different constant times a vector. If I'm trying to solve this, I'm saying to myself, can I write b as a linear combination of a sub 1 through a sub n? Or in other words, is b in the span of these vectors, a sub 1 through a sub n? This is called a vector equation. Excuse me, and this is the expanded form of the vector equation. So we can have what's called a linear system, that's right here. Or we can have a vector equation, either in this expanded form or in this shorter form. In the last video, we said that this was equivalent to this, and I think that that made sense. If we actually write this out, if we expand it, and then we add the vectors on the left-hand side, just component by component, we get this, and we set that equal to that, so that's true. Now, the third equivalent way is to take all of the coefficients in this linear system right here. and write them as a matrix. So we'll have A sub 1, 1, A sub 2, 1, all the way through A sub M 1. So you have M rows. Then we have A sub 1, 2, and A sub 2, 2, and A sub M2. So we still have M rows, but we're in the second column here. In the third column, we'd have A sub 1, 3, A sub 2, 3, A sub M3. And then we keep going. Eventually, we're in the nth column. We have A sub Mn. This is a matrix A. It has M rows and N columns. So sometimes we'll write it like that with a subscript. That's just telling us that the size of this matrix A is M by M. This is the number of rows, and that is the number of columns. If I take this matrix and I multiply by the vector with components x sub 1, x sub 2, all the way through x sub n, and by the conventions of matrix multiplication, how matrix multiplication is defined, this is actually equal to this. And we'll talk about that in just a moment. So this times this is giving me the left-hand side of the equations, that system of equations over here, and we'll set that equal to the right-hand side. So that should be an, oh, that's an n, that's right, B sub m. Now, the matrix X, or excuse me, the vector X has n rows and 1 column. So when I multiply these together, the matrix multiplication makes sense because the number of columns of this matrix is equal to the number of rows of this matrix. As long as these two middle numbers are equal, the matrix multiplication can be done. And the resulting matrix has size given by this number times this number crossed with that number. So this is A times the vector X equals the vector B. And the vector B is an M by 1 column vector. Okay, so this is called a matrix equation. So we have to talk about a few things in order for this to make a little bit more sense. But it turns out that this matrix equation has a solution, or possibly a number of solutions given by the vector X, and the components of the vector X are these numbers x sub 1 through x sub n. If the vector X has these components x sub 1 through x sub n, then x sub 1 through x sub n would also satisfy this equation. And x sub 1 through x sub n would also satisfy this linear system of equations. So we can think of this problem in 3 different ways. We can think of this as a system of m linear equations and n unknowns. So you can think of this as a hyperplane, and this is a hyperplane, and this is a hyperplane, and we can think about where all the hyperplanes on this list intersect. They intersect at a point, or possibly infinitely many points. Given by x sub 1 through x sub n. We can think of it that way. Or we can think of this problem in a slightly different way. We can think of it as asking, okay, if I have a vector b, is b in the span of the vectors a sub 1 through a sub n? Or in other words, is b a linear combination of these vectors over here? And if it is, what is that combination? What do the weights have to be? So that when I multiply the vectors by the weights and I add them all together, I get the vector b back. Like, the question is, what are those weights? So x sub 1 through x sub n here, the weights that are necessary to create this vector b are the same x sub 1 through x sub n that tell us the points of intersection of these hyperplanes. And then the last version of this is taking this matrix A and it's multiplying by a vector X. And it's saying, if you take this matrix A and you multiply it by a vector X, you get this other vector B. And we're going to talk much more about this interpretation later. Now, a shorthand version of this is this. Notice that this first column is A1 and the second column is A2 and the third column is A3. So we could just write it this way. That is just my shorthand for a column A1, a column A2, a column A3, and then we'll have a column A sub n. I'm taking that and I'm multiplying it by the vector x, which has these components, x sub 1 through x sub n. And if I do that, it turns out that that's equal to this times x1 plus this times x2 plus this column times x3 and so on, which is the expanded form of this. And that's equal to this vector b on the right-hand side. So this is another form of the matrix equation, just doesn't have all of those subscripts. Now, in order to show that this is equivalent, this matrix equation is equivalent to the vector equation, and the vector equation and matrix equation are both equivalent to the linear system, I think it's helpful to review a few things. Again, the size of a matrix, let's say, is the number of rows crossed with the number of columns. You have a memory device. I don't know if you are familiar with RC Cola. It helps people remember that we always do rows first and then columns. So if I have a matrix like this, I've got one row, two rows, and then I've got 1, 2, 3 columns. So if this is my matrix A has a size of 2 rows by 3 columns. So we would say it's a 2 by 3 matrix. And let's see. Let's say this is our matrix B. We've got 1, 2, 3, 4 rows. And we have 1, 2 columns. So this is a 4 by 2 matrix. Sometimes we'll write that the size of A is 2 by 3. Sometimes we'll write that the size of B is 4 by 2. And then we need to talk about matrix multiplication. A matrix multiplication is defined in terms of dot products. So let's say you have, let's just say, let's do a 3 by 3 matrix. And I'm not going to be particularly creative this time. I'll just make the entries 1, 2, 3, 4, 5, 6, 7, 8, 9. And let's say I want to multiply that by a vector with components x, y, and z. First of all, I notice that this is a 3 by 3 matrix. And this has 1, 2, 3 rows and 1 column. So this is a 3 by 1 matrix. So the number of columns of this matrix and the number of rows of that matrix match. So this matrix multiplication is well defined. Let's say if A and B are such that the number of columns of A is equal to the number of rows of B, then the product A times B is well defined. And then we do this, we evaluate this in terms of what's called a dot product. So what we're going to do is we're going to take the first row here and the first column here, and we're going to compute a dot product. Let's say you've got a vector that looks like this. 1, negative 2, 5. And let's say you have another vector that looks like this, x, y, and z. The dot product of those two vectors just comes from multiplying component by component and adding. First of all, notice that I've got 1 row and 3 columns here, and I've got 3 rows and 1 column there. So those match, and that means that we can actually compute this product. We can do the matrix multiplication here. The result is a single entry. It's a 1 by 1 matrix. And the way dot product works is you multiply and then add, multiply and add, multiply and add. So we're going to have 1 times x plus negative 2 times y, or minus 2y, plus 5 times z. That's the dot product. Or if you were to look at vectors like 2, negative 1, 7, and the vector 5, 6, negative 3, the dot product of these would be a single value, 2 times 5, plus negative 1 times 6, plus 7 times negative 3. And if you evaluate that sum, we have 10 and negative 6 and negative 21. So that's negative 27 plus 10. So that's negative 17. And that is the dot product of this vector with this vector. Now, sometimes when we write the dot product, we don't write it as a 1 by 1 matrix. We just say this vector dotted with this vector is actually negative 17, and it's not a matrix containing the value negative 17. But I hope that you get the idea. It's you multiply and add, multiply and add, multiply and add. So if the number of columns over here is equal to the number of rows over there, it's possible to do that. You can multiply and add, because I've got 3 of these guys and 3 of these guys. Well, then I can multiply and add, multiply and add, and multiply and add. If these numbers aren't the same, I will eventually run out of entries in the row or the column that I am working with. And we don't want that. So we need these 2 dimensions in the middle, the number of columns here and the number of rows here. We need those to be the same. The resulting matrix will have size given by this by this. So this is going to equal something. It's going to have 3 rows and 1 column. So it's going to be 1 entry, another entry, and another entry. And we can figure out what that is in just a moment. Sometimes we'll say that the ith, jth entry of AB is denoted that way. Sometimes you'll see it, well, I will just say it's written that way. This is going to come from taking the ith row of A and dotting it with the jth row of, or the jth column, excuse me, of B. And I'll show you what I mean. So if we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to make this a little bit different now. Let's say that this is a negative 1, 2, negative 3, negative 4, 5, and 2 again. This is a 3 by 3 matrix. This has 3 rows and 2 columns. Since these match, we can multiply them. And the resulting matrix is a 3 by 2 matrix. So we're going to have 3 rows and 2 columns. So I'm going to have numbers here in a first row, a second row, and a third row, and a first column and a second column, excuse me. And to figure out what goes right here, in the first row, first column entry, I take the dot product of the first row and the first column here. So I might denote this little guy over there as A sub, or AB sub 1, 1. This is the first row, first column entry of the matrix AB. So I take this row, first row, and this first column, and I take the dot product. So I do 1 times -1 plus 2 times -3 plus 3 times 5. And then we work that out. Just do a little bit of arithmetic. So we have -7 plus 15, which is 8. So that's the first row, first column entry. That goes right there. Now for the first row, second column entry, I'm going to take the dot product of the first row and the second column. So you might denote this by A sub first row, second column, rows then columns. So you take the dot product of these two guys. So you'll have 1 times 2 plus 2 times -4 plus 3 times 2. And so we get 2 plus -8 plus 6, which happens to be 0. So that's the first row, second column entry. So we go right there. And then you repeat this process for the second row and first column. Take the dot product there. That's going to go in the second row and first column. And then for the second row and second column, you use the second row and the second column. So let's see. Second row, first column will have -4 minus 15 is a -19. -19 plus 30 is going to be a positive 11. Okay. And then over here, second row, second column, we'll take the dot product of 4, 5, 6 and 2, -4, 2. So I'll do 4 times 2 is 8. 5 times -4 is 20. 8 plus -20 is -12. And then 6 times 2 is 12. So we actually get a 0 there. Okay. And then for the last row, this is the third row, first column. We take the dot product of the third row and the first column. So we do 7 times -1 is -7. Plus 8 times -3, which is -24. -24 plus -7 is -31. -31 plus 45 is going to be a positive 14. Okay, great. And then we'll take the dot product of this guy with this guy. So we'll do 2 times 7 is 14. And 8 times -30, or 8 times 4 is -32. -32 plus 14. Let's see, what is that? So we would get 18, -18. And then the last one would be 9 times 2, which is also 18. So we would have -18 plus 18, which happens to be 0. So when we do this matrix multiplication, we get this. The zeros are just a coincidence, kind of an interesting coincidence, but it's just a coincidence. That's how we do this. We just take dot products of rows with columns. So we take first row and second column to get the first row, second column entry here. Third row and first column to get the third row, first column entry here, and so on. Okay, so we can only do this matrix multiplication if the number of columns and the number of rows are the same and the resulting matrix has this size given by this many rows crossed with that many columns. Okay, so with that in mind, let's think about these dot products. If I take a sub 1, 1 times x1 plus a sub 1, 2 times x2 plus a sub 1, 3 times x3 plus a sub 1 n times x sub n, well, that gives me this left-hand side of the first equation. We set that equal to the right-hand side of the first equation. If we take the dot product of this row with this column, we get this. Great. We take the dot product of the last row with this column, we get that last equation. So it's clear that this matrix equation is equivalent to this linear system of equations. Now, we haven't shown that this is equivalent to this, but we did show last time that this was equivalent to that. If I take this vector and I multiply it by that scalar, and I take this vector and multiply it by that scalar, and I do that for all of these, and then I add them together, that's actually what I get over here. So there are 3 different ways to represent the same problem. We can think of it as a system of equations, a vector equation, or a matrix equation. Systems of equations, you think of intersecting hyperplanes. With a vector equation, you can think of whether or not this vector is in the span of these vectors, or in other words, can I write this vector as a linear combination of the other guys? And then here, we're thinking of this matrix multiplication, which we know how to do, but we really don't know what it means yet. We're going to talk more about what it means later. Okay. So let's say we have this system of equations, 3 times x sub 1 plus x sub 2 minus x sub 5 times, or 3x sub 1 plus x sub 2 minus 5 times x sub 3, excuse me, equals 9. And x sub 2 plus 4x sub 3 equals 0. That's our system of equations. We might want to write this in 2 different ways. We can write this as a vector equation. To do that, I might add an x1 term to this expression here. So then I would have x1 times the vector with components 3 and 0, plus x2 times the vector with components given by these coefficients, that's 1 and 1, plus x3 times the vector with these coefficients, negative 5 and 4. So this system of equations is equivalent to this vector equation. So we might be saying to ourselves, okay, is it possible to write the vector 9, 0 as a linear combination of these guys? And it's actually really obvious to me. Just in this form, I can tell that if x1 is 3, then I'll have 9, 0. And then x2 and x3 should be 0. And that would be satisfied. That's one solution of that system. And there may be other solutions of that system. I believe that there are. There are lots of solutions to this system. But the solutions to this problem, which is asking us if 9, 0, or the vector with components 9 and 0, can be written as a linear combination of these guys, well, that's going to be the same solution set as the solution set of these two. Now, this is a plane and this is a plane. So you might be saying to yourself, okay, well, where are the x1, x2, and x3, where those planes intersect? We've got 2 equations with 3 unknowns. And if I have 2 non-parallel planes, I would expect them to intersect in a line. So while x1, x2, x3 equals 3, 0, 0 is a solution to this, I believe that's just one point out of infinitely many points in the line of intersection between those 2 planes. So we can think of this in 2 different ways. Now, the third way that we can think of this problem is in terms of a coefficient matrix A times the vector x, where x has components x sub 1, x sub 2, and x sub 3. The coefficients over here are 3, 1, and negative 5. And the coefficients in the second row are 0, 1, and 4. And we can write this as this matrix equation. Now, the solution of this linear system can be found by using the row reduction algorithm on the augmented matrix corresponding to this, which is just like taking this coefficient matrix and then adding this vector for the solutions, or not the solutions, but the numbers on the right-hand side of the equations. So if I want to solve this system, one way that I can do it is by writing down the augmented matrix. So I write in my coefficient matrix, and then I add that extra vector 9, 0. And then I can use the row reduction algorithm to write this either in row echelon form or reduced row echelon form. Now, it's actually already in row echelon form, so I might want to write it in reduced row echelon form. So that means I need a 1 here rather than a 3, so I might replace row 1 with 1/3 of row 1. So I get that. Now, if I want this entry above this 1, which is in a pivot position, and if I want that to be a 0, so that I'm in reduced row echelon form, I need to add negative 1/3 to that. So that means I want to replace row 1 with negative 1/3 times row 2 plus row 1. So we'll leave the second row alone. And then the first row will be negative 1/3 times this plus 1. Negative 1/3 plus 1/3 is 0. Negative 1/3 times this is going to give me negative 4/3. Negative 4/3 minus 5/3 is negative 9/3. That's negative 3. And then, of course, this times negative 1/3 times 0 is 0. So we'll have a 3 there. Okay, so this corresponded to our original system. And then this corresponded to another system of equations, 1 times x1 plus 1/3 times x2 plus negative 5/3 times x3 equals 3. And then we have this last one. And similarly, we can use this to come up with a corresponding system of equations. Remember, in the first column, you have the coefficients of x1. The second one, you have the coefficients of x2. And the third column, you have the coefficients of x3. So this is saying that 1 times x sub 1 plus 0 times x sub 2, which I won't write down, minus 3 times x sub 3 has to be 4. And in the second row, we have 0 x sub 1 plus x sub 2 plus 4 x sub 3 equals 0. Now, because the x sub 1 and x sub 2 are variables that correspond to pivot columns, we tend to like to solve this system of equations for the variables in the pivot columns, or that correspond to the pivot columns, in terms of the other variables. This variable x sub 3 that's not in a pivot column is called a free variable. So if we take this, or these equations, and we solve for x sub 1 and x sub 2 in terms of x sub 3, we get this. X sub 1 is 3 times x sub 3 plus 4, and x sub 2 is negative 4 times x sub 3. And x sub 3 is free to be anything. So the solution set of this can be written this way. Sometimes we like to parameterize this, so we might say that x sub 3 is equal to t, where t is some real number. Then we would have x sub 2 equals negative 4 times x sub 3, which is t, and x sub 1 is 3 times x sub 3, which is t, plus 4. So the solution can be parameterized in this way. It's a vector x. We can think of it as a vector x with components x sub 1 of t, x sub 2 of t, and x sub 3 of t. And x sub 1 is given by 3t plus 4. And x sub 2 is given by negative 4t, and x sub 3 is given by t. So that is one way to describe the solution set to this system of equations. If you've ever taken calculus 3, you know that these are the parametric equations for a line. This is a line that passes through when x sub 3 equals 0, we get 4, 0, and 0 here. But if t takes on any other value, we're still going to be on that line. So that is the line of intersection of this plane with this plane. Now it turns out that if x1, x2, and x sub 3, if all of these guys satisfy these equations, well then we end up getting this vector 9, 0. So we can think of the vector with components 9 and 0 as being a linear combination of these guys, as long as we choose x1, x2, and x3 in just the right way. And as long as they have this relationship, we can get 9, 0 out of that. And then, of course, we could write the equation in this form. So the system of equations and the vector equation and the matrix equation all have the same solution, and we just found it. And again, the way we find it is we tend to write down the augmented matrix for the system, and then we row reduce that augmented matrix until we get usually to reduced row echelon form. And then if we happen to have free parameters, we write the basic variables. Those are the ones in the pivot columns or that correspond to pivot columns in terms of the free variables. And then if we want to, we can set the free variables equal to different parameters. So if I have one free variable, we tend to let that free variable have a parameter t, or be represented by the parameter t. So I think that's it for this video. We'll talk more about this next time. In the next video, we're going to discuss solutions, existence of solutions to the matrix equation, which is written in this form, or alternatively in this very short form, A times the vector X plus or equals B. Oops, B. So this might be an N by M matrix. This would, or excuse me, M by N. We've got M equations and N unknowns, so that's M rows and N columns. This is an N by 1 matrix with the same number of rows there. The result is an M by 1 matrix, or a column vector with M entries. So we're going to talk more about solutions of this in the next video.